Hello everyone. So today we are going to look at the solution for question number 5a posted in the tutorial. So let us look at the question again before we look at the solution. So here is the initial problem that was posted. So they ask you to solve the heat flow equation given by this expression from x going from 0 to 2 for time t larger than 0, and the initial condition is given here. So you have a u o t. So here u represents the temperature at x equals to 0, and time t, this is going to be equals to 0. And then you have another expression here, which is the time derivative of u at x equals to 2. So this is also going to be equals to 0. And then they give you another condition, that is ux at time t equals to 0 is given by 1 or 0, depending on the region of the x. Okay, so those who have not attempted this question, you can pause the video first and try to solve it before you proceed to the answer. So now let us look at how we should what we should do to solve this problem. So the first thing that I would like to do is to actually rearrange it to the normal form that we normally see, right? So normally we have on one side, on the left hand side here, we have a term which is proportional to the x, right? So this is a partial derivative of u respect to x. So this is your gradient square, right? So since this is just 1D problem, so that you have only x here. So if you have 2 dimensions or 3 dimensions, then you have to add the y and the z term. So and then on the right hand side here, you have 1 over kappa. So kappa here is the heat transfer coefficient, and then you have derivative of u, partial derivative actually, with respect to time, right? So let's write it like this. And then now we can try to solve this problem. And the first thing that we do is to actually find the solution for the steady state, right? So when you talk about steady state, it means that the solution does not depend on time. So basically your time is going to be t equals to 0. And if you recall what we have discussed previously, we have this the same picture over here. So we have a source at x equals to L, and this is going at u equals to 100 degrees Celsius, and then the heat is going to go from the right to the left, and here at x equals to 0 you have u equals to 0 degrees. And how we actually solve this is that we find the steady state solution based on these two conditions, right? So we have these two conditions, and then we are going to look for the solution in between these two region. Okay, and in this example, if you recall, we wrote the solution as a linear function of x, right? So what about in this case? So in fact, in this case, we don't have to do anything at all, because the problem has actually give you the steady state solution, right? Given here. So they actually wrote to you ux0, so t equals to 0. So basically this is your steady state solution. At t equals to 0, ux is given by 1 or 0, right? So if I do a plot, so it will look something like this. So from x equals to 0 to x equals to 1, here you have u equals to 1 degrees. And then from 1 to 2, x equals to 1 to 2, then you have u equals to 0 degrees. So step 1 completed without doing anything, because you have your steady state solution. So now let us go to the step number 2. Right, so step number 2, we need to find the solution that fulfills this heat flow equation, right? Let us just recall what we talked about in the previous lecture. We talked about using the separation of variables. So we assume that the uxt, the u, which is the temperature, can be written in a separable form. That is, you have a function f that depends on x alone, and you have another function that depends on t alone, right? So what happens is that after some derivation steps, and then you will see that you can separate it into two equations. That is, on the left hand side here, you have to solve for f, and this will give you the solution for the spatial part, and it will enter here. And the other one, which is on the right hand side here, this is the solution for the time dependent part, and the solution, if you remember, is going to be of the form like this: exponential minus kappa k squared t. So in the previous lecture, we actually wrote, instead of kappa, we actually wrote alpha squared. So in this case, instead of alpha squared, this is just kappa. So apart from that, everything is the same. So after this, what we have done is actually we have found that the solution for u is written as a multiplication of the function f that depends on x alone, and the function t that represents the time dependent part, right? So what we need to do now is to find what is fx. So once you know what is fx, then you will already solve this problem. So then we go to the second step, step 2 still, but then this is 2b. So step 2b, now we are going to apply the condition for time t larger than 0 in order to find our coefficients, right? The constants. So what do we do? Is that we will try to find the solution that fulfills this equation, and we see that the function can be either a sine function or the cos function, right? So then we use the boundary condition. So the boundary condition says that at any time t, my temperature at x equals to 0 is going to be equals to 0. So in that case, right, so where I'm supposed to put x equals to 0, and my function is going to be equals to 0. So here you will see that the cos function is not possible, because cos 0 is going to give you 1, and this is not going to lead you to having a u which is equals to 0. So here basically you strike off the solution for the cos part, right? So the only solution is now is in the form of a sine function. So now I just wrote it back again. So my uxt is now equals to sine kx exponential minus kappa k squared t. But this is not the end of the step 2, because now we have to find what is k, right? The constant k here. So in order to use the constant k, we have to look at the second condition that they give you, that is the partial derivative of u respect to time at x equals to 2 is going to give you 0. So here what you need to do is just to take a partial derivative of u here with respect to time, and this is going to be easy for you. What you will get is the same function, but then you have minus kappa k squared here, okay? And then you have the same exponential term. So this whole thing is going to be equals to 0. So now this you can just bring it down, and you will see this is equals to 0. You only have a sine kx exponential term here. And here, since my t is non-zero, so my t is non-zero, so this term can be equals to 0, right? Or if not, if this term is not equals to 0, and therefore my sine kx is supposed to be equals to 0. So in the event of a sine kx equals to 0, so my x is equals to 2 here, so I've replaced x equals to 2. So in order to have a sine k2 or 2k equals to 0, I must have k equals to n pi over 2. So now what we have done is we have used the second boundary condition in order to determine what is the constant k. So now step 2c, we are just going to write it again here. So now I know my k is equals to n pi over 2, so I can just put in sine n pi over 2x, and this is the exponential minus kappa, and this is my k squared t. But if you remember that this function is not able to represent the steady state solution. So the steady state solution now is referring to the step function from 0 to 1 and 1 to 2 in the x direction, right? So in order to be able to reproduce this steady state solution, you need to take a combination of waves, sine waves in this case, with different n value, and you write it in a series like this. So you have a summation sign here, and you have Bn. So Bn is a Fourier series, Fourier coefficients that you need to find, and you have the same function exactly like the one above, right? So now we will go to step 3, that is to determine what is Bn. So in order to find Bn, we will first set my t equals to 0, okay, and then we are going to equate both solutions that we got from the steady state and the case where it fulfills the heat flow equation, and we are going to equate them together. So here my steady state solution is given by this this term here. So from 0 to 1 I have 1, and from 1 to 2 this is going to be equals to 0. And now I'm going to find what is Bn. So in order to find Bn, I will multiply both sides by a sine function, but it is going to be sine n pi over 2. But you see that this sum here is going to go from n equals to 1 to infinity, and there will be a time where n is equals to m. So when n is equals to m, then you will see that here you have integral. So you want to integrate both sides, right? So when you integrate both sides, you have an integral sign here, and ux0. So I just retain ux0 because this value is going to change depending on your region of interest. And here you have a sine n pi over 2x, and on the right hand side you have Bn as usual. Summation sign is going to be cancelled out due to the n equals to m condition, and then you have a sine squared. Okay, so now you need to solve these two sides in order to find what is Bn. Now on the left hand side, let's look at the left hand side first. You see that this integration is going for the whole the whole range of x that is going from 0 to 2. But then you will remember that the initial condition was that from 0 to 1 you have ux equals to 1, whereas from 1 to 2 you have ux equals to 0. So now it means that you have to do this integration by steps, right? You have two different regions. And since this is equals to 0, so you don't have to do anything for this, and you just have to solve for this part, that is the integration of sine n pi over 2x from 0 to 1. So this is rather easy to be done, right? So this is the expression that you need to solve. And here I will just leave the derivation for you. It shouldn't be too difficult, and you should get a Bn equals to 2 over n pi, and in the parentheses 1 minus cos n pi over 2. So n pi over 2, this is not vanishing because the different value of n is going to change this term. So finally we have the solution for the heat flow. So my solution that we want now is uxt. So we put Bn here. So this is from Bn that we have found here, and sine function, and then as well as the exponential minus kappa k squared t. So this is the full solution that we want. So what I do next in the next two slides is to actually show you what it looks like on the plot, right? So based on the equation that we have generated just now. So here I just want to show you the effect of using a larger n value, right? So if you use small value of n, your result is not going to be accurate. So this is very obvious if you consider n equals to 1 here. So what I did was to actually put kappa equals to 1 and t equals to 0 into the equation, and I compute the uxt depending on different value of n. So for n equals to 1, so this is the expression that I will have for time t equals to 0. Okay, and you see this is just not correct, because if you compare this to the initial condition that you want, this is not true. So what I do next is to increase my n equals to 10, and I will have a plot that is represented by the red line here, and n equals to 20, which is represented by the yellow line, and n equals to 30, which is the one given by the purple line here. So here you see increasing n will give me a result which is closer to the my initial condition, right? So so this is the plot. So this is on the y-axis here, this is my temperature uxt, and this is going to be my x on the x-axis. Here you will see the temperature is 10 here. So in this region the temperature is 10. So here of course this is larger by an order of 10, by one order, sorry by an order, because in the initial condition this is supposed to be 1, right? So here you have to kind of like decrease the values by dividing them with 10, so that you have 1 over here. So but the most important thing is that you manage to reproduce the initial condition that you want, except that the values is going to be slightly different. And lastly, in this slide, I show you the plot at t equals to 0, 0.2, 0.4, and 0.6 as a function of x, right? So now what we have done previously was to show that for n equals to 30, this is going to give us more accurate results. So I'm retaining n equals to 30, but then I'm going to plot for different t values. So this one, the one in blue here, this is for t equals to 0. So we see that at t equals to 0, this looks like the step function that we wanted. And then when you go to t equals to 0.2, you will see this is the temperature across the bar. So this is the x-axis is representing the x term, and t equals to 0.4 is going to decrease, and 0.6 this is decreasing furthermore, right? So yeah, so that is the plot that we get when we use this equation that we generated earlier. The most important thing, I guess, is to actually show you that at t equals to 0, that is during the initial state solution, right? Using n equals to 30 or even larger value of n will give you a nicer initial condition that you wanted. Okay, so so that is how you solve the tutorial number 5a, and that is how it looks like on the plot. So that's all from me. So thank you very much.